So, but as a transition to that, I want to pick up something we did last time and kind of take it in a new direction. So, last time we had defined a type of trees in Disco, where you said, well, a tree can either be like a leaf, just like a, nothing under it, and we represent that by a unit, or it could be a pair of trees, right? And so we'll write that as tree times tree. So, and I think, I guess last time I had like some pictures, but, so for example, one, well, I can have a leaf, which is just left unit. Here's another tree, which is like right, so it's a pair of trees, but maybe the left one is going to be left unit, and the right one is going to be, well, maybe they're both right. So this is kind of the simplest tree that's not just a leaf. It just has two subtrees, but they're both leaves. Right? Or we could have, I don't know, make one more. Right. Maybe the left tree is a right. Or actually, we'll just say right. One. Right, we can do that. So this one has two subtrees. The right one is a leaf. The left one is this, which is itself a tree with two leaves. So this one looks kind of something like this, and this one looks something like, like this. This one is just like, okay. So. Here's my question. So obviously this is the only tree that, this side is just a leaf. And if we don't want a leaf, but we want something that just has a single branching point, right? This is the only way we can do it. We have the branch and then we just have two leaves. So here is a tree with two branch points, right? There's at least one more, right? What would that be? What would be another tree with two branch points? Does my question make sense? And maybe forget about the disco, just think about the picture. Like, here I have a drawing of a tree. It has two, like, here's a point right at the top where it branches off into two, and here's another point where it branches into two. Is there another picture I could draw of a tree that would also have 2 points where it branches off?
Like just the same thing, but like on the right branch.
Yeah, so like if this thing is over there instead of over here, does that make sense? Yeah. So that, we could write that down. And so here's a tree that's like this. This would be like right. And actually, let me switch over and we'll. assume that if there was another one, that someone in the room would have thought of it by now. May or may not be. No, it turns out, yes, this is actually all of them. There's no more. And we could keep going, right? We could say, well, what about the 4 branches? Turns out there's a bunch more of those, and we would probably pretty quickly stop being confident that we had thought of all of them, right? And also, is there some kind of pattern in terms of like how many there's going to be? So something fun I can do. Let's write a disco function that will output all the trees with a certain number of branches. Okay, so, whoops. So let's call it trees of size. And it's going to take a natural number, that's the number of branches we want, and it's going to return a set of trees. Okay, so generate a set of all possible trees with a given number of branches. I'm not going to make you write this. I'm going to just talk through how we're going to make it work. Being able to write this function is not the point, although in theory you could. But we could use it to actually look at some bigger trees and see how many there are. So okay, first of all, the base case is easy. If we want 0, there's only one way to do that. We just make a leaf. That's the only way to make a tree with no branches, right? So we have a set containing just a left, or I can even say, because I defined leaf above. So there's only no. Okay, now, if I have n plus 1, well, I'm going to have a branch point at the top to start. So that's 1. And then I claim, here's how we're going to do this. Think about the 2 subtrees of that top branch point. If there's going to be n plus 1 branch points total, there's one at the top, and then there has to be n somewhere else. And basically I can choose, how many of those n branches am I going to put on the left, and how many am I going to put on the right. So, in this, like here, there's one at the top, and then if I want 2 more, in this case I chose to put 2 on the left and none on the right. And here's also 2 on the left and none on the right. But I can also put 1 on each side, or I can put none on the left and 2 on the right. I want a set of, it's going to be, right, say LR, and we want to figure out, okay, what are the left and right subtrees going to be? So first of all, I'm going to choose how many branches I want on the left and how many I want on the right. So we'll say K is going to set from 0 up to n. Because the number K is going to be the number, or I'll say K is the number of branches that are going to be on the left. And we could have 0 all the way up to, we could have n. And then I want to say my tree on the left is going to be one of those trees that has K branches. So we say trees of size K. And then the thing on the right is going to be one of the trees of size n minus K, because that's how many branches we'll have left over to put on the right side. Okay, again, we'll come back to this, and we're gonna talk about this in more detail, like next week probably. It doesn't matter whether this code exactly makes sense to you. You can just kind of get the general idea. The general idea is, right, we're saying we have 1 branch at the top, and then we're putting some number of branches on the left and some on the right, and we're kind of doing that in all possible ways. For now, you can take my word for it. Well, we can try it out, right? So if I load. I can say trees of size 0. That makes sense. It's just left unit. Trees of size 1. There's that one tree that's it's a pair to right. It's a pair of leaf. if I say trees of size 2, it gets a little hard to read these. So I'm not going to keep doing this too much longer, but we can look at it. So this is right, where the thing on the first one is just a leaf, and then the thing on the right is is this thing. So this is the one that has the branch on the right side, and then here is the one that has the branch on the left side. But the more interesting thing is I can see how big these sets are, right? I could ask for 3. I can't read that, but if I can ask for the size, hopefully it should be 5, because that's what we drew all of them and convinced ourselves that. So indeed, they're 5. Ask what about 4? It turns out there's 14. Size 4. We ask about size 5. It turns out there's 42. Let's see. I'll do 6 and I'll talk about it while it's working. It's going to take a while, but it wasn't that long. 132. So there are a lot of questions we could ask here. Like, is there a way that we could? Well, certainly, is there any kind of pattern here? Like, what numbers are these? Is there a way that we could figure out those numbers without literally drawing all the trees? Or is there some kind of systematic way that we could know that we had gotten all the trees? So that's kind of what we're going to be working towards. So we're going to start talking about something called Combinatorics, which is basically the mathematics of counting things. And counting things doesn't sound like it would be that interesting. Like, okay, I can count. I've been able to count since I was like 3 or whatever. But figuring out how big some set of things can be interesting if the set of things itself is interesting. And this, it has a lot of important applications, such as, it comes up a lot if you're analyzing some kind of algorithm where you have some kind of input and you're like, how many possible inputs are there? Or how many possible things are there? If I'm going to like loop over all these possibilities, how many are there? How long might that take? It comes up a lot in probability, where you say, okay, like how likely is this to happen? Well, that depends on kind of how many possible things there are that could happen, and how many ways there are for this thing that I care about to happen. And you have to count those so that you can figure out, okay, well, there's 24 ways for the thing I want to happen and 157 possibilities, so that's the probability, 24 over. Those are just a few of the places this comes up. So, Combinatorics. So it's all about counting. Or another way to say it is finding the cardinality of finite sets. Like maybe you're given some set, or you're given a description of a set to figure out how big it is. So this comes up in probability. Analysis of algorithms, etc. It's also just a fun and beautiful area of math. I mean, people have been doing this for a long time. Really, probably some of the first, what we would think of as recognizable combinatorics was done in the surface of probability. I mean, in a larger sense, like, people have been doing things that we would recognize as combinatorics for thousands of years. So the other thing I want to mention is that it's quite possible that you memorized a few combinatorics formulas in high school. So if you ever learned about like combinations and permutations, stuff like that, right? Like on your calculator it says NCR or NPR, or like factorial, right? It doesn't matter if this rings a bell or not. I'm I'm saying it's possible that you've memorized some formulas about this. But the goal here is our goal is going to be to learn some kind of general principles that you can apply to a lot of scenarios, and in fact you could use to rederive those formulas that you might have memorized. So there are going to be some formulas, but the goal is not to memorize a bunch of formulas. The goal is to understand where they come from and be able to apply the same principles to other scenarios. Okay, and that example we did about trees, we're going to come back to that once we've developed a bunch of techniques and principles. We'll come back and reanalyze that, and there's a lot that we can figure out about that. We'll see that we can actually figure out how many trees there are of different sizes without listing them all. All right. So we'll start with a simple principle today, which shows up all over the place. So this is product rule. So, one thing I'll say first, before I tell you what the product rule is that often when we're talking about these different rules and principles, instead of talking about the size of a set, we'll talk about the number of ways to choose an element of the set. Now those are the same thing, right? If a set has size 10, then there's 10 ways I can choose one of the elements of the set. But for whatever reason, I've found, and I hope you find too, that it's kind of psychologically easier somehow to think about actively choosing something than it is to think about just like counting how many there are. I don't know why that is. It's like if you think about I'm actually doing something, then I can think about, okay, what options do I have? How would I go about doing this? How can I break it down into steps? As opposed to just saying like, there are some things, I must passively count them, right? So I'm always going to phrase things in terms of like choosing things, but it's the same. So let me just, we will usually talk about the number of ways to choose an element rather than the size of the set. Right, but they're equivalent. Okay. So without further ado, let me tell you what the product rule is, and then we'll look at a bunch of examples. So suppose that choosing an item can be decomposed into two independent choices. With, say, C1 ways to choose, or to make the first choice, and C2 ways to make the second choice. Then, the total number of ways to choose is C1 times C2. I like to think of this in terms of a grid. So if each box represents a thing I could choose, right. So each grid square represents a thing I could choose. And in order to choose something in the grid, right, I can say, well, independently I get to choose what row I want and what column I want. And when I say independent, that means which row I choose and which column, like which row I choose has no effect on which column I'm allowed to choose. And vice versa, right? I can choose any row I want, and then regardless of which row I chose, I can now choose any column I want. And every choice of a row and a column uniquely determines, one of the cells that I've chosen. Okay? And obviously, if you have a rectangular grid and there's C1 rows and C2 columns, then the number of grid squares is C1 times C2. We've all known that since, whatever grade that was that you learned the area of a rectangle. Or this is just like what multiplication means. Right? So independent means the choices don't affect each other. Right? And in terms of the picture, the fact that they're independent means it's a perfect, exact rectangle. Right? Something that wouldn't be independent is like, imagine that these two grid squares didn't exist. Well, then that means, okay, if I choose this row, then I actually can't choose these columns because those don't exist, right? Choosing this row means I'm limited in which columns I can choose. They're no longer independent, right? They affect each other. But if it's a perfect, complete rectangle, then totally independent. I can choose whatever I want. Okay, so the independence is very important. And that's definitely something, when you think about this rule, you have to think hard about whether the things are really independent or not. Because it often might be that you can decompose something into two choices, but if they're not quite independent, then you can't exactly use this rule. There are ways around it that we'll see in certain scenarios, but the basic rule is if they're totally independent. Okay, and really, this boils down. We can see this as an instantiation of the fact that the size of a Cartesian product is the product of the sizes. Right? Why is that? Well, think about my choices C1 as the set A, and my choices C2 as the set B. Right? Then, like, choosing one of these things corresponds to, making a choice, choosing one of the things from my set A and choosing one of the things from my set B, and that gives me a pair of them. And this is saying, what's the total number of kind of independent choices you can make from A and from B? Well, it's just the product of their sizes. Kind of the same idea, but in a different format. Okay, any questions at this point? Or I'm going to do a bunch of examples. Okay, I'll just do some examples. And that may spur some additional questions. Start with something simple and we'll work our way up. So there are 3 kinds of cereal and 7 kinds of fruit. For breakfast, you must, I don't know why must, who's making the rules here, but you must choose one cereal, cereal and 1 fruit. How many breakfast choices do you have? Right, probably you all would have been able to answer this before I talked about the product rule. Kind of like, well, obviously if I can choose 3 different kinds of cereal, and independently I can choose 7 different kinds of fruit, like all the combinations, there's 21 possible combinations. you could draw it in a grid and think about like, well, this column is all this, frosted flakes, and this column is Cheerios, or whatever, and then the fruits are the rows. Right? 3 times 7 equals 21. Or I'll just say choices. Okay. Here's another example. Same as before, except, oops, if you choose oatmeal, then you can't have peaches or bananas. Now, you all could probably figure out what the answer is in this case. That's not my point. My point is just, in this scenario, the choices are no longer independent. Right? This is kind of like what I said before. We took some cells out of the grid, because now, when I choose oatmeal, that affects what fruit choices I have. So we cannot apply the product rule, at least not directly. So this is kind of I would say, a non-example. We can't apply product rule directly, since the choices are no longer independent. I mean, yes. In this example, it seems clear that we've just basically removed 2 choices. We've removed oatmeal and peaches and oatmeal and bananas, so we can just subtract 2 from 21. And that's correct, but we'll come back to that later. Oh, what? That's very odd. Okay. I guess I was like looking over my lecture notes before class, and like, okay, it makes sense. But I think the version of them that I have on this device is like an older version, and it just stops here. So I guess no, I'm just kidding. I'll make something up, or I kind of remember what it was. It doesn't really matter. So let's see, another example. How many 2-letter strings are there? Let's say with only uppercase letters, uppercase English letters. Right, so for example, AA would be such a thing, or like, HX would be one, or QB, etc. So what do y'all think? How many total 2-letter strings would there be that I could make? I don't know.
Are we only limited by the alphabet?
Yeah, you can only use capital letters A through Z.
Okay.
Jason?
576?
Well, you actually know the square of 26. And you have that. Yeah. I mean, yeah. So how did you get 576? You did 26 times 6.
26 letters.
Yep, that's right. So yeah, the way that the product rule applies is I have 2 independent choices, right? I can independently choose what the first letter is going to be, and I can choose what the second letter is going to be. They're independent because there don't seem to be any rules like restricting how the letters can be combined. I can have anything for the first letter, anything for the second letter. So 26 times 26 says we can independently know, so for example, I could have AAA, or I could have HDX, or I could have, XYZ.
It's going to be 26 cubed.
26 cubed, right. And technically, right, the product rule kind of only says what to do if you have like two choices. So one way we could think of this is, well, I actually could break this into two choices. I could say, well, first, I'm going to choose what the first two letters are going to be. And I already know there's 26 squared ways to choose the first two letters. And then I can independently choose the third letter. So we could say there's 26 squared ways to choose the first two letters, and 26 ways to choose the last letter, and hence it's going to be 26 cubed. But in general, I think this example shows that we can generalize the product rule to any number of choices. If I have a whole bunch of choices and they're all independent, I just multiply the number, all the numbers together. Right, so, more generally, you could say there are 26 to the fourth, 4-letter strings, and 26 to the n letter strings. And we can generalize the product rule to any number of choices, any number of independent choices, still have to be independent. Right, we just multiply them all. Okay, let's see. Another example. License plates in Arkansas. And again, ignoring lots of real-world things like there's probably certain combinations that they don't allow, and there's like custom license plates, whatever. Ignoring all of that, they consist of 3 digits plus 3 letters. Right, how many are there? How many possible license plates are there? I mean, not how many actual license plates are there. That's a different question. We cannot answer that second question with math.
Yeah. 10 cubed by 26 cubed.
I did, right? We can, all the choices are independent. The digits give us 10 choices each, and the letters give us 26 choices each. So I don't know what that is. That's probably it's maybe around 1 million. I don't know. This doesn't seem like enough, actually. Okay. Another example. How many subsets are there of a set of size n? And we have actually already talked about the answer to this question, but I want us to see what the product rule has to do with it. Does anyone happen to remember the answer? Maybe it's just as well. If you don't remember the answer, we can figure it out using the product rule. How can I think of this? So think about choosing a subset I have a set of size n, and I'm going to choose a subset of it. How many ways do I have to do that? And how can I think of breaking it down into independent choices? Okay.
Could we, like, do the same product rule on each of the sides? Like each of the sides up to n, kind of thing? No.
I don't know what kind of choices you would be thinking of making. So if I have a set, let's say 1, 2, 3, has a bunch of possible subsets. You know, I could have the empty subset. I could have 1 and 3. I could just have 1 and 3, 2 and 3, just 2 by itself. Right? There's a bunch of different subsets I could do. The way to think of it in terms of independent choices is, for each element of this set, I can choose whether to include it in my subset or not. And do you all see that those are independent? Right? Like, whether I include 1 or not in my subset doesn't affect whether I'm allowed to choose 2 or 3. Right? And any combination of choices will result in some subset. So for each element, I have 2 choices. Right? I can either include it in my subset or not include it in my subset. So for each element of the set, we can independently choose to include it in a subset or not. Okay, so that's 2 choices, and right, we have n of those choices, right? So the total number of choices is, well, I have 2 choices for that first element, times 2 choices for the second element, times 2 choices for the third element, dot, 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 times 2, and I have n of these, which is 2. For example, how many binary numbers are there with n bits? Okay.
And this just like any of the above, because every bit is going to either be 1 or 0.
That's right. Yeah. These 2 examples are really kind of the same thing. Yeah. You know, different guises. So yes, I have n bits. For each one, I can independently choose whether I want it to be a 1 or a 0. So the answer is going to be the same. And I think we did actually talk about this before, right? We could take each subset and identify it with a string of bits, where each bit, like 0 means that element's not in the subset, and 1 means it is in the subset. Right? So like, with that set 1, 2, 3, like 1, 1, 1 would mean I have all the elements. You know, 0, 0, 1 means I only have the 3, and so on. So it's the same. You know, each bit, or I'll say we can independently choose each bit to be 0 or 1. So given 2n choices. Okay. Let's see. Here's another example. You have 10 different cans of soup, as one does. And you plan to eat one per day. And the question is, you know, how many different soup eating schedules could you make? So at first you might think, well, let's see, I've got 10 cans of soup to choose from. I've got 10 days, so it's just going to be like 10 to the 10th because, you know, each day I get to choose one of the cans of soup. That's not quite right though. Why not? Adam?
For each successive day, there's one less option.
Yeah, right. So like, as I just said it, that doesn't work because the choices are not independent. I can't independently choose any one of the 10 soups every day because some of them are gone. I can't choose them. It might seem like, oh, we just can't use the product rule because they're not independent. But I think what you were saying, Adam, shows that we kind of can do it if we change our perspective a little bit. We say, well, you know, after the first day, one of the soups will be gone. It doesn't really matter which one. The point is I'll have 9 left. And among those 9, I can choose any one I want. So that, like, choosing among the 9 that are left is an independent choice from the first choice, right? Because I don't know exactly which soups will be left, but I do know there will be 9, and that I can choose any of those 9. So I'll have 9 choices, even though like the actual specific choices I have might be different. But that doesn't really matter if we're just trying to count them. So on day 1, we have 10 choices. On day 2, we have 9 choices. Right, we can choose, you know, any of the soups that are left. Right, and so on. On day 3, we'll have 8 choices, you know, etc. On day 10, we'll only have 1 choice, which is, you know, whichever the one that's left, that's the one you're eating today. You don't get to choose. I mean, you already made your choice, right, by eating the other ones. So, so the total number of choices is, of course, 10 times 9 times 8 times ... times 1, right? Or we could write this as 10 factorial. Right, and in general, this argument shows that n factorial is the number of ways to put n different things in a particular order. This is also known as permutations. So again, maybe if you've heard that word in high school or something. Right, a permutation, it just means an order. So the total number of permutations of n things is n factorial. But you don't have to memorize that, right? If you know the product rule, you can kind of do this reasoning and figure out why that's the case. Because you say, well, I choose n things to go first, and then I have n minus 1 choices for what's going to go second, and so on. And they're intermittent. All right. Any questions about